The module is split into 4 parts, if you remember. And the first part is about random events, where we do counting, define events, look at axiom, Bayes rule, and independence. So we're done. That's us finished that part of the module. And now we're going to go on and have a look at the second part, which is random variables. And that leads on to a bunch of things, so mean and variance and correlation and actual statistics and so on. So let's look at random variables. So up till now, we've only looked at random events, and a random event can take any kind of value. If you remember, a random event is a subset of the sample space, so it's a set. And the elements of sets can be anything. It could be heads or tails or colour or an age or the weather or anything. And one of the, that's powerful of course, but one of the downsides is we can't do calculations using events. You know, it's meaningless to add heads and tails or to add blue and green. You know, that doesn't make any sense. And so if we want to do calculations, we have to have numbers. And so it's quite like typing in programming. You know, the random events are ordinal types, and we're limited in the operations we can do with them. What we'd like to do is define a real value quantity or an integer value quantity that's linked with a random event, so that we can carry out calculations using it. And that's what a random variable is. A random variable effectively maps every event to a real number. So an example, an important example, is an indicator random variable. And that's one that takes a value 1 if an event E occurs, and 0 if the event doesn't occur. So that's like a really strong mapping, straightforward direct mapping between an event and a number. Another example might be if we have 2 coin tosses, then the random variable might be the number of heads, number that come up heads. So what we're doing is we're taking the event heads tails and mapping it to the value 1. We're taking the event heads heads, mapping it to the value 2, and so on. Or when you throw a dice, what's the sum? And sometimes it's a bit confusing. For example, when you throw dice, the events seem like numbers, the random events seem like numbers. You know, we could throw a 1 or a 2 or a 3. And then we're going to map that to a number. But it's not really, it's actually a set, right? The random event is really a set, whereas the random variable is really a number. So what we're still doing is mapping from a set to a number. But it's worth being conscious of that that's what you're doing. Otherwise it can get a little bit confusing. Okay, so a random variable is a function that maps from the sample space to a real number. So a random variable is a function, which is quite a strange thing in itself. And if we're being formal, we would write a random variable x as x is a function of omega there, so it's some Greek, where omega is a subset of the sample space, so it's an event. So x is a function of random events. But it's very common, like almost universal, just to drop that omega and write x. And think of the number being linked to the event, but it's worth bearing in mind that that's just a convenience. It's really a function, it's really a mapping from events to numbers. Because it's good to know what the quantities you're dealing with are, and otherwise, you know, it's quite easy to get confused. You know, if someone asks you, it's a popular interview question, what's a random variable or what's a random event, and you don't have an idea because you've got some intuition but you never made it crisp, then you're struggling, right? Whereas it's worth being clear on what these quantities really are. Now, when the value x can only take a fixed number of values, so for example 1 or 2 or 3 or something, then it's a discrete random variable. Otherwise, if it's properly real valued and can take any value, then it's a continuous random variable. Now we're going to focus primarily on discrete random variables because we can get nearly everything we want using them. But after the midterm, towards the end of the last quarter really of the module, we'll have to look at continuous random variables And they're not any harder really than discrete random variables, but the notation is more daunting and looks messier. So we'll put that off till a lot later and focus on discrete random variables. All the ideas that we need we can get from discrete random variables, and they're just easier to work with. So back to our indicator random variable that takes value 1 if an event E occurs and 0 if it doesn't. Sometimes, so I won't do this, but sometimes you might see random variables defined in terms of events. So that's not a random variable. If you see someone writing a random variable x is equal to sandwich, right, where it's your lunch, then that's not real valued, so it's not officially a random variable. But what might, that's a fact, right? But what might be being meant is that it's an indicator random variable that takes value 1 when event sandwich occurs, and otherwise 0. And it's just a shorthand, but it might not be, so it's worth being aware of what's going on there. I certainly won't do that, but you might see that in some books and so on, some stuff on the web. So let's look at some more examples of random variables. Suppose we do 2 coin tosses and the random variable is how many come up heads. Let's call that our variable capital X, and the usual convention is to use uppercase for random variables to distinguish them from scalars, because remember the functions are these odd quantities. They're distinguishing from normal numbers that we'll use lowercase for, and I'll stick with that convention. So here X takes values 0, 1 or 2. The sample space is pairs of heads or tails, so it could be heads heads, heads tails, tails heads, tails tails. And we're going to map from this sample space to 0, 1 or 2. And so what we're doing is saying when we get the event tails tails occurs, we're going to map that to the value x equals 0. When the outcome is heads tails or tails heads, then so that's either of those events we're going to map to x equals 1. And when the outcome is heads heads, we're going to map that to x equals 2. So you can see how we're creating a function that takes every element in sample space and maps it onto a number. But it could also be that it maps subsets, groups of them when it's mapping, like for example, if it was an indicator random variable, mapping a subset of events onto a number. Suppose I throw a dice, 2 dice, what's their sum? So it can take values, a random variable can take values from 2 to 12. 1 is impossible because we're going to throw a minimum of 2 ones, which is 2. Our sample space, so this is one example where it's a little bit confusing because the sample space and a random variable both look like they contain numbers, and they do, but it's all the ideas still carry over. So we've got a sample space where which contains pairs, a 1 and a 1, a 1 and a 2, up to 6 and 6. And then we associate x with the outcomes. So if the outcome is 1, 1, then x is 2. If the outcome is 1, 2, or 2, 1, then we map it to x equals 3, and so on, and we're back to having the function that maps. And in general, if we've got a random variable x equal to a value x, see I'm using uppercase for the random variable and x for the actual value, which might be 1 or 2 or whatever, then we can define a set of events, which is a set of outcomes of the experiment for which the random variable is equal to the value we're interested in. So for x equals 3, the set of events that correspond to that would be 1, 2 and 2, 1. So that would be the set of events that are associated with each value, with the value of a random variable, with value 3, and so on with value 4 and 5 and so on. And so that's important because it means we've got a really strong link between the probability of values of a random variable and the probability of random events that we've already looked at a lot. So we can say the probability that x is equal to x, little x, is the probability that this event occurs, that one of these outcomes occurs. So the probability x equals x is the probability of this E sub x, the set of events that map onto the value little x. And that means that when we're working with random variables, okay, they're numbers, which is what we want, but all of our ideas from random events carry over without any change. So let's just work through that a little bit, just really quickly. So for, if you remember, for random events, this is the definition of conditional probability. And so we can write the same thing for random variables. So the probability x equals x given y equals y, so these are numbers, is equal to the probability x equals x and y equals y over the probability x equals y. That's just mapping these numbers of the random variable onto the corresponding events. So this comes exactly from that. So for example, if we roll 2 dice, what's the probability the second dice is 1 if both sum to 3? So let's define some random variables. But because the choice of mapping from events to numbers is arbitrary, right? You can pick it whenever you're whenever you're working with random variables, you have to define what that mapping is. And you should do that when you're answering questions. Otherwise, if you just write down X or Y, I wouldn't necessarily know what you mean. So it's worth being careful in actually defining what you mean. So let's consider random variable X, which is equal to the first value rolled, and Y is equal to the sum. Then the probability we want is the probability X equals 1, probability, I've said the second dice is 1, and the probability that the first one there, so that's a typo. So we're interested in the probability x equals 1 given y equals 3, given that they sum to 3. So the probability x equals 1 and y equals 3, the probability of the first dice is 1 and they sum to 3 is the probability of the event that you threw a 1 and then a 2, which is probability 1 over 36. And the probability that they sum to 3 is the probability of the event that you get a 1 or a 2 or a 2 or a 1. So that's 2 over 36. That's the probability that you throw a 1, the first one is a 1, given they sum to 3, is the probability of x equals 1 and x equals 3, which is 1 over 36, divided by the probability that y equals 3, which is 2 over 36. 36 is cancelled and you get a half. Marginalization carries over. So we can map from these joint probabilities or from conditional probabilities to unconditional probabilities. So if we've got probabilities like this, probability x equals x and y equals y, and y, all the possible y's values are y1 to ym. Now they're necessarily disjoint, right? We the event that we get a y1 and equal to 1 and y2 equals 2, those can't overlap. So and so we can sum over all the possible values from 1 to m of y, and then that gets rid of the dependence on y, and you're just left with probability x equals x, just like we did with random events. And the proof is the same. So do have a look at the proofs, but I'm going to skipping over them now. But you shouldn't skip over them. You should work through them and try and understand them. Don't memorize them. Memorizing them is a bad idea. But they're very straightforward, and it's worth reading them and trying to get the idea behind them so that you understand what's going on. Because conditional independence carries over, then the chain rule carries over. And so does Bayes' rule. So the chain rule for random variables is, the probability x equals x and y equals y is the probability x equals x given y equals y times the probability y equals y. So it's just follows directly. It's directly analogous to what we did for random events. If you remember how we derive Bayes' rule, that means that immediately we get that the probability x equals x given y equals y is the probability y equals y given x equals x, probability x equals x divide the probability y equals y. So we can move around the conditioning from here, from probability y equals y given x equals x to probability x equals x given y equals y. And again, it just carries directly over from our ideas from random events. For independence, we use the same approach as for random variables. Probability, the definition of independence is the probability x equals x and y equals y. It's the probability x equals x times probability y equals y if x and y are independent, and only then. And that follows directly again from the ideas from random variables, so everything carries over. So once we've got this idea of mapping from random events to numbers, we can import all our ideas from random events over conditional probability, general, marginalization, Bayes, independence, and just get imported directly into random variables.